Chapter 1. Mid-Write Failure. We start with a concrete scene, a creative workstation freezing halfway through a multi-gigabyte export and the file system reporting I/O errors, not a GPU or app crash. Vendor TBW, total bytes written, labels and teardown photos then show the same drive later with remapped blocks and the failing flash channel, which is a common trace in endurance reports from independent test suites. Mechanically, an SSD failing mid-write usually signals exhausted program erase cycles or severe write amplification that filled spare area. And that failure mode is different from spinning disks. It's about cells no longer reliably storing voltage states. The takeaway is immediate. Beyond headline sequential speed numbers, cell chemistry and endurance specs predict whether an SSD survives heavy sustained writes. Chapter 2. Flash Families. To reason clearly, we define the families. SLC stores 1 bit per cell, TLC stores 3 bits, and QLC stores 4 bits. NAND vendor datasheets and JEDEC-related white papers document typical program erase cycle ranges and error correction needs for each family, which set the era and capability bounds. The mechanics are straightforward. More bits per cell mean narrower voltage windows and higher sensitivity to noise, so error correction and wear leveling must work harder. For visuals, imagine spec cards with PE cycles and ECC margins. Our portable rule is that bits per cell compresses cost and endurance into a single trade-off axis we can read on a datasheet. Chapter 3. SLC Basics. SLC historically offered the highest endurance and fastest raw write speed, often rated in tens to hundreds of thousands of PE cycles in older vendor datasheets and used in enterprise caching or industrial modules. Controller white papers show SLC's simpler voltage states reduce ECC overhead and lower write amplification, letting controllers manage fewer remaps and faster garbage collection. In practice, SLC appears today mostly as expensive cache layers or as standalone industrial drives, not mass-market NVMe parts. The takeaway? For write-heavy databases, log drives, or intense caching, SLC or pseudo-SLC modes are the safest choice if cost allows. Chapter 4. TLC Trade-offs. TLC, the mainstream choice since around 2015, sits in the middle on cost and endurance and is the default for most consumer and many data center SSDs according to vendor product lines. Datasheets typically list PE cycles in the low thousands for modern TLC, paired with ECC algorithms and DRAM-backed mapping tables described in controller papers. Mechanically, TLC often uses an SLC cache to absorb burst writes and then flushes to denser TLC cells, which improves perceived speed but hides sustained write limitations. The portable rule: TLC is excellent for mixed consumer workloads and many server uses, but you must validate sustained write patterns and warranty TBW to be safe. Chapter 5. QLC Realities. QLC is the densest, lowest cost per GB option, and vendor presentations emphasize capacity economics and cold storage use cases, with typical PE ratings often below 1,000 cycles. Controller white papers and teardown analyses show QLC relies heavily on advanced ECC, stronger over-provisioning, and larger SLC caches to meet performance expectations. In practice, QLC suits read-mostly archives and bulk storage where occasional large writes are acceptable. The takeaway? Use QLC for capacity-first scenarios and avoid it as the primary scratch or VM data store unless you accept higher failure risk and plan for frequent replacements. Chapter 6. DRAMless versus DRAM SSDs. We see a clear microstory in product tiers. DRAM-backed SSDs include onboard DRAM for the flash translation layer, FTL, mapping table, while DRAMless designs either embed the map in NAND or lean on host memory buffer, HMB, features in modern NVMe drivers, as controller spec sheets and vendor notes explain. The mechanics matter. DRAM holds mapping entries for fast random writes and low write amplification. Without it, the controller must access NAND to find mappings, multiplying writes and increasing latency. Independent benchmarks and teardowns consistently show DRAM-less parts performing acceptably for everyday reads, but struggling under sustained random write workloads. The takeaway is simple. For heavy write servers or intensive creative workloads, prefer drives with onboard DRAM and documented mapping behavior. Chapter 7. Over-provisioning and firmware. Over-provisioning, the spare NAND area reserved for wear leveling and garbage collection, appears in vendor spec tables as a percentage or user-adjustable slice. Controller firmware uses this pool to smooth writes and remap failing blocks. Mechanics from controller white papers show more OP lowers write amplification and extends usable life, but it comes at cost of usable capacity. Similarly, power loss protection and firmware defenses reduce the chance of mid-write corruption. Enterprise datasheets often list capacitors and recovery algorithms for this reason. Our practical takeaway is to consider effective over-provisioning when comparing drives. Buying a slightly larger capacity drive or enabling extra OP often yields much better endurance than chasing nominal write speeds. Chapter 8. DWPD, TBW, and the math. Vendors publish TBW and sometimes DWPD drive writes per day in product specs, and converting between them is straightforward for procurement conversations. For example, a 1 TB SSD with a 600 TBW rating and a 3-year warranty translates to about 0.55 DWPD, because DWPD equals TBW divided by capacity and warranty days. Endurance test suites and vendor logs confirm these calculations predict real-world lifespans if we match workload patterns. The mechanics behind TBW use PE cycle budgets, spare area, and write amplification factors from controller models, which is why two drives with similar TBW numbers can behave differently under mixed or sequential workloads. The thumb rule. Compute DWPD from TBW for your expected daily writes, and pick a drive with a comfortable margin rather than the bare minimum. Chapter 9. Synthetic benchmarks and counterexamples. Synthetic benchmarks are valuable, but they often hide real behavior by testing short bursts to an SLC cache or using unrealistic queue depths. Independent endurance tests and teardown logs document drives that post excellent crystal disk mark numbers but collapse under sustained host writes once the SLC cache fills. A counterexample is a high-capacity QLC drive that posts desktop-like sequential write numbers using a large pseudo-SLC cache, yet heat and sustained writes expose higher error rates and slower garbage collection in long-duration tests. The mechanics behind these traps are write amplification spikes and FTL pressure. The takeaway is to insist on sustained, long-run benchmarks or vendor endurance tests that match your workload profile before procurement. Chapter 10. Procurement SLAs and Final Synthesis. For procurement and replacement planning, we recommend concrete SLAs. Require published TBW and DWPD values tied to warranty terms. Specify minimum OP percentages or equivalent usable spare area. Demand power loss protection for critical writes, and ask for sustained write benchmarks or vendor endurance logs that match your workload profile. Vendor data sheets and endurance suites should be listed as receipts and contracts. In practice, choose Enterprise TLC or SLC-backed parts for VM hosts and active databases, Mainstream TLC for mixed client fleets, and QLC for read-heavy cold storage with scheduled refresh cadence. Our final synthesis names the pattern plainly. Bits per cell defines a predictable trade-off axis. More bits means more capacity per dollar and less endurance per write. And controller, OP, and DRAM determine the real-world lifespan. One memorable rule of thumb: if your daily writes approach even 20–30% of a drive's DWPD, plan on an enterprise tier part or a refresh cycle, because endurance and firmware, not headline speeds, protect your data. If you want to continue, our next video breaks down M.2 form factors and thermal throttling, which helps decide not just which NAND you buy, but where to put it.